So it's great to see so many of you here. Thank you very much for coming, and hello to everybody who's joining us online. So maybe you think that I am an astronomer, and therefore I enjoy being up late at night, looking at the stars. But actually I'm not really an astronomer. I'm an astroparticle physicist, and I don't use normal telescopes, so I don't need to work at night. So this is as exotic for me as it is for you. But I would like to share some of my research, current research ideas with you. And if you were able to put on a pair of glasses which was sensitive not to visible light but to X-rays or even higher energy light like gamma rays, this is how the sky would look. It would be a fantastically interesting view that you would get. And you would see that the sky is glowing in gamma rays. There will be persistent objects which glow all the time in gamma rays. You can see some of them here. You would see the Milky Way as a glowing band here as cosmic ray particles interact with the material in the disk of our galaxy. And now and again, a few times a day, you would see intense flashes of gamma rays on the sky, so-called gamma ray bursts, where in a few seconds you release as much energy as the sun releases in its entire lifetime. Extraordinarily interesting events. And yesterday we found out that we're entering a new era in astronomy, and for the very first time, certain objects, these very short gamma ray bursts, were observed for the first time, both in electromagnetic radiation, in that case gamma rays, and also as gravitational waves. And this was the very first time this has been done, and this opens a whole new chapter in astronomy. But we're not quite finished with standard astronomy using electromagnetic radiation. And normally in astronomy, one points one's telescope at some object, say this object here, which happens to glow very brightly in X-rays, and one characterizes that radiation in terms of some kind of spatial image. You make a picture. You can also look at how the radiation varies as a function of time, a so-called light curve, and you can measure the energy spectrum of the energy which is released, the radiation which is released. But as you probably know, electromagnetic radiation is a manifestation of an electromagnetic wave, and that can also have a polarization. And this polarization is not normally measured, and this is what my research concerns, trying to measure this polarization to help us understand objects on the sky. So in this little animation here, you see an electromagnetic wave. This is a polarized electromagnetic wave. It's vertically polarized. This means that the electric field oscillates only in the vertical direction, as you see here. And this is normally what's not measured. So normally, as our eyes are completely insensitive to polarization. We can use fancy filters to figure out what the polarization is, but inherently our eyes cannot determine the polarization. It's the same for most telescopes which are used in astronomy. And this is a shame because the polarization encodes very important information to do with what's going on in the sources, in these very exotic sources, which I'll talk about in a moment. So it can tell us, for example, about the processes which give rise to high energy radiation. It can tell us about the geometry of the material in the sources, which we simply can't see with standard telescopes. And so, for example, it can tell you about how magnetic fields are organized in the sources. It can tell you about how material is organized, and the polarization, if you can measure it, gives you a very good insight into these quantities. So I'm particularly interested in two very interesting sources, very bright sources in X-rays. One is the Crab. This is the remnant of a supernova which occurred in year 1054. And the other is a so-called black hole binary system, where you have a black hole here which is accreting, which is sucking matter off a supergiant star in which it forms a binary system. So these two objects are the two objects which I've studied with my research group over the last few years. So in order to study such objects, you cannot just go out and buy a telescope from your local hardware store. You have to build one. And this took us some time to do and some time to get right as well. This has been quite a journey. And here you see the telescope which we have built, and you'll see immediately it doesn't look like a normal telescope. I mean, where do you look through? How do you know? It's not a standard telescope. So this is a telescope for determining the polarization of X-rays from objects on the sky. And as you probably maybe can guess here, this thing is lifted up outside of the Earth's atmosphere, because the Earth's atmosphere protects us from X-ray radiation from space. So you must make the observations outside of the atmosphere. And this is then done not with a satellite or a rocket, because that's very expensive, but instead we use an enormous helium-filled balloon. And this balloon contains 1 million cubic meters of helium gas, and that's roughly twice the size of Globen, the Globen Arena in the south of Stockholm. So it's a huge balloon. And then this balloon can lift our telescope up above the atmosphere to about 40 kilometers altitude, and from there we can make our observations. And luckily in Sweden we have a very good place to do this. Of course you can't just release such a balloon in the middle of Stockholm. That would be kind of unpopular. So instead we go to the north of Sweden to the S-Range Space Center, and there's lots of area where you can make such experiments. So we developed this telescope in collaboration with industry partners, the Swedish Space Corporation, SSC, and also a small company in Linköping called DST Control. And here you see the telescope, and it's inside this machinery here which allows us to move the telescope up and down and to swing it under the balloon to follow sources as they move on the sky. And there's lots of other paraphernalia around. You have to be able to produce electricity, so there are solar cells, there's GPS systems, so you can figure out where you're pointing. So it's quite a complex piece of machinery. So often in space contexts, you hear the phrase, failure is not an option. Well, I have experimental proof that in fact failure is an option, and it happens quite often when you're doing difficult scientific tasks. And we failed several times. And this is part of our journey. So we tried first of all to fly this balloon in 2010, but we were not able to because we needed to borrow some equipment from NASA. They had an incident in Australia, which is a fancy way of saying a crash of one of their balloons, and the equipment was impounded. We could not use it. So we tried again in 2011, and this shows the launch from S-Range, and we got off the ground, but unfortunately the wind changed direction and it increased intensity unexpectedly just after the balloon left the ground, and the balloon was damaged. We got to about 30 kilometers height, and then the balloon had a hole in it and the flight stopped. So we had to try again. We got the equipment back to the ground with a parachute. So in 2012 we went back. See, we're very persistent. We went back in 2012 and we waited for about 6 weeks, and it rained more or less the entire summer. No launch. We went home. We went back in 2013, and then we had a nice flight. So actually then we had permission from Russia to fly over Russian airspace. So we launched here from S-Range, and we flew around on the stratospheric winds during July, and we flew around, and actually we landed in Siberia here. This wasn't planned, but the wind was changing direction, and we had to come down here. And we made some first measurements using our telescope, and these were eventually published. So this showed us that our measurement technique was okay, but we could improve it. So then last year, 2016, we made our most successful flight. This was a 5-day flight where we launched here from S-Range on July the 12th, and then 1 week later, we landed on Victoria Island in Canada. So the balloon launch is shown here, just after launch. And then this shows the balloon when it's fully inflated at the top of the atmosphere. So at launch, only the top part of the balloon is filled with gas, and then the balloon expands as the payload rises up in the atmosphere. Here's a nice image taken out through the aperture of the gondola, and you see here that this curvature is just a feature of the camera that was used, but you see very clearly the very thin atmosphere here, which protects the Earth. And then finally, this is the landing, and this is a good landing in the balloon business. So it looks quite like the payload is quite damaged, but the purpose of this shell is to protect the telescope, which we've been lovingly building over the last few years before the launch. And then we could get this equipment back to Sweden, and in fact we got the data back within about a week after the landing. We could start to do the analysis and start to make scientific results. And you can look for a very nice video on YouTube if you search for Pogo Plus, P-O-G-O plus. And you'll see a video where the entire flight is shown. The 5-day flight is condensed down into about 7 minutes, and you can follow the balloon as it travels 40 kilometers above the Earth's surface, and you get some very nice footage from the cameras on board. So of course it's not just me doing this work. I have a very good research group who helps me, and here they are. So this is the campaign team that was up in S-Range with me. So it's PhD students, postdocs, researchers, our industry colleagues, our colleagues from Japan. And actually, looking at this picture, it's an important reminder of how we do science these days. I mean, we have to collaborate, and in this picture there are, even though we're a relatively small group, there are 8 different countries represented. So people here have heritage from 8 different countries, and we all collaborate together for a common goal to try and understand these objects on the sky. So the project was funded by the Wallenberg Foundation, by the Swedish Research Council, and most importantly by the Swedish National Space Board, the Swedish Space Agency, who have provided very good support for all this very long journey to finally making successful results. So let's take a look at what we found out then. So this shows the crab. This is the aftermath of a supernova which occurred in the year 1054 and was recorded in historical writings. The supernova was actually then rediscovered in 1731 by an English astronomer. And this is a so-called multi-wavelength image where you see, as you move out from the outside in, you go to successively higher energies. So you start off out here in radio, in a kind of reddish color, then you move into green, the optical, and then finally the bluish color is X-ray emission. So as the emission energy increases, you probe closer and closer in to the energetic object, which is at the center of this supernova, which is called a pulsar. And this pulsar can accelerate subatomic particles like protons up to very high energies, so-called 10 to the 15 electron volts, which is higher than the highest energy particle accelerator we have on the Earth at the moment, which is the Large Hadron Collider at CERN. So buried in the middle of this expanding shell of gas, there is a rotating neutron star, a pulsar, and this is an extremely interesting object. So this is a star, a type of star, which is primarily composed of neutrons, unlike day-to-day material which we experience, which is protons, neutrons, and electrons. So it's a neutron-rich object. It's rather small. It's about 15 kilometers in diameter, so quite small. But it weighs about 1.5 times the mass of the sun. So it's extraordinarily dense. So if I was able to send Christer Fuglesang to this star, that'd be difficult because it's 6,500 light years from the Earth, and he was able to stand on the surface of the star and dig out 1 teaspoonful of the material here. That teaspoon, when he brought it back to Earth, would weigh the same as 1 million cubic meters of rock. Sorry, 1 cubic kilometer, 1 cubic kilometer of rock, which is about 1 billion tons. So it's extraordinarily dense. And not only that, it's rotating around an axis here about 30 times per second. And as it does so, it spits out high energy radiation, X-rays and gamma rays along the magnetic axis here, which is displaced from the rotational axis, just like our own Earth. So it's an interesting object, but we don't really understand how the high energy radiation is produced and where in this object, where in the so-called magnetosphere, the magnetic field associated with the pulsar, where the high energy radiation comes from. And polarization can tell us about this, and this is why we want to do these measurements. So this rather technical figure shows what we published in the journal. The details are not so important. What you see here is this is one rotation of the pulsar, one as it rotates round. And you see this blue curve here is how the intensity of the radiation changes. It pulses, hence the name, as it rotates. And what we do is you measure the polarization at different points in the rotation. And the important thing to take away, well, there's 2 important things. One is that this is the first time that the polarization of the electromagnetic emissions in the X-ray band have been measured. And the second thing is that you would perhaps think that the polarization would be very, very small, because this is a very chaotic object. You can see here there's lots of, it's a very chaotic cloud of gas and magnetic fields, all very, very entwined. You would think that the polarization should be very, very low. But in fact, it turns out that it's rather high. It's of order 20% or so. So 20% of the photons of this electromagnetic wave oscillates in a defined plane. And this is quite surprising. So it indicates that the emission arises from an organized area, a magnetically organized area. And this must be rather small then. So we can compare this to images taken with standard satellites. This is from the Chandra X-ray satellite. So the pulsar is in the center. It's not this bright spot, but it's near to this bright spot here. And you can see with these imaging X-ray telescopes, you get these fantastic views very, very close into the pulsar, where you can see what you're seeing here is X-rays emitted by electrons, which are gyrating around magnetic field lines. And as they gyrate around the field lines, they release so-called synchrotron radiation. And you can probably just about make out these kind of toroidal structures here. And the idea is that the electrons are trapped in magnetic fields in toroidal trajectories, somewhat like plasma trapped inside a fusion reactor, inside a tokamak. And when they're trapped, then they release this synchrotron radiation. And by measuring the angle of the polarization, the angle at which the electric field is oscillating up and down, we can confirm that this is the correct hypothesis, that the electrons are indeed trapped in these toroidal structures. So we shed new light on these objects, which otherwise are somewhat difficult to understand with standard techniques. Another exciting object which we're studying is this black hole binary. So this is a so-called binary system. So it's two objects which are orbiting around a common point here in the center, and they orbit once every 6 days or so. And these are, extremely heavy objects. So this is a supergiant star, which is about the same mass of, it's about 30 solar masses. And this black hole here has a mass of 15 times the mass of the sun. And matter from these are sufficiently close that matter from this supergiant star is accreted, as we say, or sucked into a disk around the black hole. Okay, and as a result, this matter falls down into the black hole, releasing potential energy, which then manifests itself as these two jets, which fly out in equal and opposite directions to conserve momentum. And if you look at this, this is clear. This is an artist impression. So this is not what you see if you look through a telescope. This is purely an artist's view of how this should look. It looks like a point on the sky. So we're trying to understand the geometry of this system. And we can do this with polarization. This is what we're currently studying. And what we find out is that the level of polarization is very low from this object. And this allows us to very tightly constrain geometric models for this object, which is called Cygnus X1. And we can learn more about this object than we can by making simple X-ray observations. So this is currently ongoing research. We're currently writing papers and trying to get them accepted in scientific journals. So these are the two objects which we've been studying with our balloon-borne mission. And of course, we think now we understand how to make these measurements, and we'd like to take the next step. And the next step would be, it would be very nice if we could do the measurements on a satellite. So a balloon is a very good way of developing instrumentation. But if you launch a balloon from the north of Sweden, you can only fly for about 5 days or so until you have to cut the balloon down. And at the moment, that's because the balloon will eventually enter Russian airspace, and you don't want to do that. So you stop the flight before then. But there is an opportunity to fly on a satellite, and the Swedish National Space Board have a so-called InnoSat satellite program. And this is a small satellite platform. It's something like a washing machine size, onto which you can bolt a scientific payload. And there's an open competition, so groups can propose payloads to the space agency, and then there's a review process. And at the moment, so we have been selected, along with 2 other missions, both from Chalmers, and both the other missions are looking down at the atmosphere. We're the only mission looking up into space. And we proposed an instrument that you can see here, which we've called Sphinx. And this is an instrument to measure the polarization of the X-rays produced in these gamma ray bursts, these intense flashes of gamma rays on the sky, which last just for a few seconds, but where more energy is released than the sun releases in its entire lifetime. So these are fantastically interesting astrophysical events where enormous amounts of energy are produced. And we'd like to understand how this energy is produced. And one way to do that, or one part in the puzzle, is to measure the polarization of the emissions. And this is what we plan to do with Sphinx. So we're currently competing. We're hoping we'll be selected. And if we're selected, we will start to build this at the beginning of next year. And the launch will be sometime around the end of 2021 or the beginning of 2022 or so. But I guess this is really another story. And I won't say I'll wait 100 years until I tell you about this But maybe I can hopefully tell some of you about this in the very near future. I'll finish there. Thank you.